Hi, everyone. First, thank you for coming. This is incredible. There's significantly more people than I ever expected. Yeah, full house and overflowing. Amazing. Right. Okay, should I take my mask off to speak? If people are okay with that. Okay. Yeah, so meet Lucy. Lucy is the name of our quantum computer, and we're going to go through how to build a quantum computer on the hardware level. So comparing the classical hardware stack and the quantum stack at each stage and seeing how they compare. So I am a software engineer at Oxford Quantum Circuits. Just for a bit of background on me, I come from an academic quantum theory background. I then spent some time as a web developer, and now I'm at Oxford Quantum, merging these two fields of my life. If people are interested in getting involved just in the quantum world, there is no unique path. As I'm sure many of people in security know, a long time there was no fixed path into security. It's the same in quantum. It's very nascent. If you're interested, yeah, you can get involved. Yeah, so who we are, we're based in Reading, which our taxi driver thinks that a 30-minute train makes it a suburb of London. It is its own town in its own right. But yeah, we're based in South Reading. We build quantum computers from there on site in Thames Valley Science Park. And our goal is to bring quantum computing to as many people as possible. That's very important to us. We don't want to lock it away behind excessive paywalling or exclusive access. We're trying to bring it to as many people as we can. There's a lot of chat on the democratization of quantum computing. We want to bring it to as many as we can. So a quick run through of the timeline of our company. QCAS, so quantum computing as a service. We delivered this in July of 2021. From there, we launched on AWS in February of this year. So you can, at any time, if you have an AWS account, log into the Bracket service and access our computer through there. And yeah, we're the first, not just first, we're the first non-North American company. We're quite proud of that. And we've just finished our Series A round of 38 million. So we're going to do some very exciting things. Now we've got a big chunk of money under our belts. With the University of Tokyo, which, if anyone knows, as VC goes, they do very strict due diligence. So we've had our credentials tested. Cool. So here's a quick system overview. What does hardware companies? Sorry, before I get going, I want to say, any questions, just raise your hand. I'll get to them. This is meant open discussion on hardware. Any questions, throw them up. If you're on the Quantum Village Discord as well, there is a Lucy channel. Throw them in there, and there'll be someone keeping an eye on. So if you don't want to speak out loud, you can throw it in our Discord, and I'll answer those as well. Cool. So the hardware stack. At the minute, this is Lucy, a picture of Lucy. As you can see, this, you don't really get a scale, but that's a full server rack. And so this fridge, that bit is the fridge. It maybe stands 3 meters tall. So we're, in the old IBM mainframe days where you're taking up an entire room for your computer. We maybe have 1 or 2 server racks and a massive fridge. So not really something we can put in people's homes yet. So cloud access is the main way. There are a few places that will put a quantum computer into a certain premises for direct access. But for us, cloud access brings it to as many people as possible. But that's access. Then we hit the actual quantum computer. So you hit our compiler first. That's where I spend a lot of my time working on the quantum compiler. So we'll take a look at some QASM. Mark showed this earlier. This is quantum assembly language. We are very much in the assembly era of you declare a register and you operate on bits and you declare individual operations. So we take that in our compiler, we perform many transformations and optimizations, and spit out some, bytecode effectively. Then we have the control stack. So that's what you can see here on the left side, this large server rack. This is what actually controls and manipulates the state of the quantum computer. So this is all FPGA driven, all, custom firmware and logic, and then microwave control lines and readout. So our I/O is, very simple. We basically have an in and an out, and that's your I/O. And then finally, the actual QPU. So quantum processor unit is the analogous to the central processor unit, and that sits about there, and that's where the actual quantum magic happens. Sorry, I shouldn't say magic. It's not magic or woo. It's very easily understandable. If I say magic, someone tell me off. Okay, getting right into the very lowest layer, the QPU architecture and layout. So this is very much analogous to classical transistor design and CPU layout design. So at Oxford Quantum Circuits, we are a superconducting qubit company. Quantinuum are also in the room. They're speaking after me. They're an ion trap company. Being British and BBC, other hardware providers are available. But yeah, we do superconducting. I'll go into that in a minute. And this is the same level as the transistor in your CPU. So that's where we are designing effectively what the transistor looks like. I'll go a bit later. So this is our core IP. It's called the Coaxmon. So you notice our qubits, there's the blue Transmon. Our control port and our measurement port are coaxially connected. So they come in from the top and the bottom. So instead of our microwave lines have to come in like transversely, and you have to route microwave lines through one another, we just connect straight through into the top. And that means that as we scale out, we're not having to redesign microwave control lines every time we build a new processor. We just go horizontally. So this is what I think of as cloud horizontal scaling. And then next we'll go into CPU setup. But yeah, so what this gives us as well, one issue we'll go into, these are microwave drive pulses. That's quite hard to contain. So when you have fields coming in sideways, you get leakage, right? You drive one qubit and another one is impacted. And so we have very, very low crosstalk, which is a big source of noise from this architecture, and we get scaling. I said you have ion traps, which Continuum use, and you get photonic-based systems as well, diamond-based systems. So diamond, you have a nitrogen instead of a carbon, and a gap where some electrons stick out. And then you have that is a qubit as well. So some solid-state devices are coming up as well. So what is a qubit? It's a two-level system. So you think of a binary bit, you have 0 or 1. In a quantum system, in a qubit system, we also have 0 or 1, but we also have the superposition of 0 and 1, which is partly where the quantum power comes from. The main point you also have is entanglement between two qubits, which is where you have greater correlations than is possible classically. Continuum will go much more into the algorithm side of quantum computing. But what we do is we create a two-level system. There's effectively what a transmon is an artificial atom. And atoms, you have a ground state in an atom, and you can excite it into the first excited state of the atom. Those are our two levels in a quantum system. And we're building fake atoms in order to make these qubits. Okay, so the next step, once we have decided on our transistor or our qubit architecture, we have to connect them up. And this is very much, the analogy here is your CPU layout. There's a lot of cool images now of the new M-series atom processors and how you arrange the different cores you have. And it's something quite similar here in how you connect up your computer. So one thing that we don't get in quantum computing that you get in classical computing is trivial, not trivial, but easy individual addressability of bits. Every bit, so this is one qubit 0, 1, 2, 3, 4, 5, 6, 7. So all these individual qubits need to be addressed individually. And if you remember, we drive these things so we drive a bit flip from 0 to 1 with a microwave pulse. In order to maintain that, when you drive a single qubit, it only drives that qubit, they need to be addressed on different frequencies. And those frequencies are determined by the properties of the transmon. So different widths and different fabrication processes change the frequency with which it's addressed. And so there's an interplay here. So continue will go into entanglement. So we have a sense of 2-bit operations. Effectively, if you want to interact 2 bits, if you do that on a classical computer, you don't think about this. You want this bit and that bit, you just do that. We can only do that between directly connected qubits in superconducting architectures. And so we have to design quite carefully that there's a trade-off between wanting very high connectivity, where you can interact 2 bits freely, but you also don't want to cause collisions. You don't want to accidentally start addressing surrounding bits when you're trying to drive one. So there's different solutions to this. IBM have gone for this heavy hex lattice. Google, in their Advantage paper, they went for this layout. And at the minute, we have 8 qubits live on AWS, and we have gone for a ring. And this is going to, you'll see a lot of change in this in the future, especially when it comes to quantum error correction, which I'll touch on a bit later. But this is still very active. There is no, clean sense of control unit register combination logic you get in a CPU. We're still working that out, and every generation of quantum processors comes with a new connectivity architecture. Cool. Any questions? Yeah. Sorry, I can't hear. Would you like? You can come and ask it so everyone else can hear as well. This is an open chat, so you can ask questions. Question here as well.
So my question is, each transmon has 8 qubits entangled. 8 ions or whatever entangled with each other, and you have an array of transmons. So, how many, qubits simultaneously do you have?
Yeah, cool. Thank you. Thank you for that. I wasn't super clear on this. So, a transmon, they're both just rings. So, a transmon is effectively a single bit. That is 1 qubit. And on a single computer, we have 8 of these right now. So we are at the 8-bit stage computing. IBM are pushing just above 100 at the minute. And yeah, but we're a much younger company than them. We'll outscale them, don't worry. So this array that you see is the future plans. I should have been clear on this. This horizontal scaling is where we will go. Yeah? Right now we don't have that, but we will be scaling out in, we'll be growing soon. And will it look like a soccer ball? Who knows? So this is something that is designing this, what this connectivity looks like. It requires input from the entire hardware stack. Because myself on the compiler team, I want the highest connectivity possible. And then the fabrications scream at me when I ask for all-to-all connectivity. So it's finding that balance between the optimal at every stage of the hardware. Cool, good question, thank you. Fabrication, we have to make this now. So at Oxford Quantum Circuits, we do all of this, by the way, so we fabricate as well. And this is in clean rooms. It looks very much like your fabrication for a classical process. It has lithography and etching. And this is really hard. This is nanofab. So this is these things are you're fabricating on nanometer scales. You've seen how I've CPUs are at 5 nanometers. Someone scream at me if they're much smaller than that now. The fact that they've got this process so slick has taken a very, very long time. And every time you introduce something new into a quantum process, you're having to redesign your entire fabrication process as well. So this step looks quite similar. The processes are slightly different to classical CPUs. That's largely economies of scale, from what I gather. This step looks similar. It's in a clean room, lithography, etching, very, very difficult. Huge respect for our fabrication engineers. They do an incredible job. Cool. So that is the quantum processor unit. Yeah. Yeah, so the question is, we are available on AWS. Is our computer with them or is with us? So our computer is housed in our offices in Reading, and they cloud access through us. And one thing it is all, anyone that uses it, our entire data pipe is based within England. So the data containment and security is very important. So that's the CPU, effectively. Before we move on to the control stack, which is something like the motherboard, are there any questions on that? No, cool. So, controlling these things. So we have bits, and we have bits that are connected, and that is something like a CPU. Well, now we want to change them. If you can't manipulate your bits, they're useless. You have some static bits floating in the ether. So this is what we refer to as classical control hardware. This is this very large server rack that has microwave lines going out and readout lines coming back in. I'd say this is something like the motherboard, because in terms of design, this has to manage, the controlling of the CPU. This is why it's if you saw architectures, it probably looks nothing like a motherboard, but it's the closest analogy we have. So we have a lot of RF engineers, a lot of superconducting companies will, because as I said, these are microwave lines. They are fiendish to control and manage very cleanly. And then it's all fed through classical control stack. Sorry, I'm waffling. Let's get back. What are the challenges with the classical control stack? So this is all FPGA based, and it has to be quick. So let's say absolute upper bound for the industry for a single qubit gate, so like a NOT operation is 100 nanoseconds. And let's say for a 2 qubit gate, so interacting 2 bits, let's say 800 nanoseconds. Those are rough industry upper bounds. So that means if you want to do an if statement, a very core component in computing, you have to read out your bit, process it classically, and then feed back a new instruction within 30 nanoseconds. That seems fine for classical compute, right? You can do that sort of thing, but everything takes time here. When we read out the state of a qubit, that takes time as well. And whilst time is happening, everything else is being affected by the environment. It's something we'll go into with quantum computing, is that it's very noisy. It's very, very sensitive to noise. And so we're constantly battling to try to counteract the effects of noise. So that as you leave your system running, idling, as you're doing some compute, it's decohering. It's becoming less useful. Lots of errors are coming in. Yeah, so that's our control stack. Right now, the control stacks are working very cleanly, very quickly. What we're seeing as the future, the next step for a lot of things is mitigating these errors in the control level. But also, after this, I'll show a little video on the sort of dimensions that we're looking at for things. There's a limited amount of bits you can fit into one of these fridges, right? You maybe have that much space to stick bits. Once you scale, you have to start networking these fridges together. And that means you now have a highly distributed system. You have this distributed FPGA control system. That's a big challenge to write and write that quickly and communicate information across your system. So if we have a quick clip to show the size that we're operating on. So this is about just under 2 centimeters squared. And there is a qubit sat within that square. There's the Transmon and the measurement side. Control lines come in coaxially. And this is the connection I was on about. It's a physical capacitive connection that has to be fabricated into the CPU, the QPU. QPUs. So this is not what we have at the minute. This is how as much as we can scale on a 2 centimeter squared wafer. That goes into its housing, and there. So that's the sort of size scale that we operate on. And after that, you have to start distributing your system, which has its own series of challenges. Cool. So again, any questions on the classical control stack? Yeah. Sorry, I can't. Yeah, good question. How long does it take to read out the state of the qubit? It's a good question, because it's one of those things that depends how clean you want it. It can vary. So if you Continuum, they have trapped ions, so they can really flood their system and really let it saturate for microseconds. I'm not seeing any shakes from Continuum. I'd say around, let's say, upper bound about a microsecond for an absolute max upper bound, generally speaking. But it's one of those things that's a big area of research in terms of how to measure your qubits cleanly and in the shortest amount of time. So it's going to come down very rapidly very soon. Yeah, it will start to come down in the future. Cool. So the compiler. So this is why. Oh, sorry. Yeah. Yeah, great question. How long do qubits stay in their state after you modify them? So we call this coherence time. So this is how long are your qubits useful for? And so for a superconducting architecture, 50 microseconds-ish. So that gives you a rough ballpark of how many operations you can put into a coherent window. But that varies from, within the industry, that varies from 20 microseconds to 100 microseconds. Yeah, so formal operation, upper bounds for superconducting qubits industry, let's say like 80 to 90 nanoseconds for a 1 qubit gate, and upper bound 800 nanosecond for a 2 qubit gate. Yeah, so so the question was, how does your gate time scale as you add more bits to the gate? So in classical logic, you can do any on any number of bits and say and on many, many bits. For us to do a 3-bit operation takes a lot longer than just scaling. But there are some very neat tricks where you can actually get 3 qubit gates to run really, really fast. There you have to play some clever tricks with getting gates to run simultaneously and such. But it doesn't scale pleasantly because you have to take like 6 2-qubit gates to do it. So it's 6 times the length. Yeah. Yeah, so that question was about scheduling gate operations effectively. How many gate operations can you do simultaneously? So for a superconducting architecture, as long as we can do as many gates simultaneously as we'd like, so long as there's no overlap in bits. So I'll go in the compiler. There's a scheduler that shunts as many things simultaneously as possible. There are other architectures like ion traps where they have gate regions, and Quantinuum can do 5 gates simultaneously at the minute. So different architectures have different amounts of simultaneous operations they can perform. Yeah, so it was the number of bits you have on a single wafer is the number of times, roughly how many you could do simultaneously. Cool. So the compiler, this is where I spend most of my time. I'll check time. Cool, 30 minutes so far. Yeah, I could talk about this for a long time, and please ask me questions throughout the weekend on this. This is where I get most excited. This is OpenCASM 2.0. This is the current industry standard for an interoperable assembly language. So we have some headers. OpenCASM 2 include a standard library of gates. And then you can see the level we're working on. We are declaring a QReg is a quantum register, and a CReg is a classical register. So you're saying, give me 4 qubits and 4 classical bits. Because one thing to note is we can't directly read quantum information. You measure a quantum bit, and it collapses to 0 or 1. And so that is a classical bit. So we convert this quantum information to classical information and output it into a classical register, which is then read. So H, Q0, CX, Q0, Q1, CX, these are bit-level quantum operations that we're performing. And then you measure the entire quantum register onto the classical register. So this is human readable. And we take this human readable code, we do our compiler steps, and you get results. So what does this result output look like? It's bit strings. So when you measure 4 qubits, every bit collapses into 0 or 1. So you have a 4-bit bit string output for 4 qubits. Cool. So what does our compiler look like? It's CAT, Quantum Assembly Toolchain. V1 we called internally Ragamuffin, because it was a bit of a ragamuffin to get going. We are very much taking inspiration from classical compiler toolchains. So that's why I go compiler the compiler. If you know about classical compilers, there's a lot of the same things going on in quantum compilers, because we need that for scalability and optimization. So we take QASM. Shout out to Quantinuum. We use Ticket, which is their open source library. Woo! And that's routing optimization and directionality. I'll touch on that again in a sec, that's important. AST, we have a generating AST, generating a tonal representation, code generation step for our firmware level. This gives us quantum instruction set. validate, and then this is where we do scheduling, which I mentioned before. Have all the operations, how many can you do at the same time? And then that gives you a series of pulses. Give me a Gaussian for 3 nanoseconds on this bit. Give me a square microwave pulse for 20 nanoseconds on this bit. So if we go back to the first step, this is routing, optimization, and directional gates. Who has cared about register allocation when they're coding? There's a few. It's exciting. You don't really want people to care about those things, right? Or which buses are connected on your CPU. You don't want to care about any of the underlying architecture. So that's what this routing step does. We flick back. So let's say I want to do a 2-bit operation between qubit 4 and qubit 2. There's no direct connection there. I can't do that. Luckily, there's a quantum swap operation, which you can literally swap the state of 3 and 2. So that's what this routing layer does. If you ask for an interaction between 2 and 4, it will swap 2 and 3, do the interaction, and then swap them back. And that's so that people can write algorithms agnostic of hardware. Because it's one of the bad things about writing at assembly level. This isn't true assembly level because it's quite interoperable. One of the worst things about writing assembly level, if you want to port it to a different hardware, well, good luck, you know? So we're trying to abstract that hardware step away. Optimization goes into squashing the number of gates you have. So this is the same as any, LLVM optimization pass that removes dead code. We have very, very similar dead code removal. The directional gates, again, so actually, strictly speaking, this diagram has a directionality on it as well. You can only really do like 0 to 1, with 1 being the control and the target for conditional flips. We manage that because that's a frustrating point to deal with, right? That's quite hard. So one thing I'd like to talk about that's quite exciting in the community is the future of quantum compilers. There's a very big, I've mentioned LLVM briefly, and that's because there's a big effort in the community to around something called QIR, which if anyone has worked with the LLVM IR, it's the quantum version of that. So can we roll our quantum operations into LLVM IR and perform optimizations using the LLVM toolchain? And that's a big community effort. So there's people from Oxford Quantum Circuits and IBM and Rigetti. Microsoft are playing a big part. Quantum Machines, Continuum. It's a big community effort because we want everyone to use it interoperably. We don't want people stuck writing code for one piece of hardware and then never be able to use their algorithm again. And also there's 30 plus years of compiler expertise that we can lean in on. Why are we going to write constant propagation when it's as good as it gets in LLVM? So we're really leading into the classical compiler toolchains. So what we need a lot more of classical compiler engineers for optimization passes. Count next. Cool. Any compiler questions? Yeah. The question was, can we see the quantum instruction set? No, I'm sorry. This is where it becomes proprietary and quite sensitive for us. But it's a description of pulses. I can certainly say that. It's a description of microwave pulses. If you would like to see a description of, I'm not Wi-Fi connected, but you can look up quantum intermediate representation, which is the current proposed quantum instruction set for something similar. Cool. So now we've left the hardware stack, and now this is software concerns for the hardware. So this fridge, this is the fridge that Lucy sits in. By the time you get to the lowest level, you're at near absolute zero, minus 273 degrees. You're at millikelvin. So imagine that's a big engineering operation to first get to that temperature and then maintain it 24/7. And so there's a lot of bespoke monitoring and alarms you have to build into your hardware that you don't need to think about with your classical hardware. The biggest temperature concern is in Las Vegas and your iPhone says, please stop using me, I'm at 48 degrees. We're at the very opposite end of the scale with that. And of course, network stability and bandwidth. Cool. And then the final layer within the hardware is the access layer, which is QCAS, our Quantum Compute as a Service. We're available on AWS. And yeah, it's super no frills, very small, keep it clean, keep it very fast. So that's the stack. So what? What have we done? We've got a fridge to near absolute zero. We've designed a qubit and its connectivity. We fabricated the qubit. We've housed it in a dilution fridge. We've designed our microwave setup, our control lines, our FPGAs. We've compiled the FPGAs. We've built the compiler. And we set up the cloud so people can use it. Okay, now what? Who cares? Now what do you do with it? Well, there's one more step that we need to do, which is calibrate these things. So one of the big challenges that we have versus classical compute from a calibration standpoint is the fact that we have continuous values. We're no longer binary. So you can gap your binary bits by 5 volts. Then you're fine with calibration. Your noise has got to be pretty bad, to start interfering. But we have continuous values, so that becomes a real calibration difficulty. So the frequency, phase, amplitude, pulse width of all these microwave pulses are something that we control and manipulate in order to give very high fidelity. So that when you do 0 to 1, you want to actually get a bit flip. Just calibrating a bit flip is a big challenge in terms of shaping your microwave pulses correctly. Yeah, and you'll see in very sophisticated calibration routines, these microwave pulses are not just Gaussian, they change on the nanosecond scale. Great, so now we can do these operations cleanly, throw them through our stack, and you get your results back. So, notable omissions I'll go on to. That's our stack and using it. The next section I'm going to talk about some omissions and the future of quantum computing hardware. So any questions on the stack up to that point? No. Cool. We'll go on to omissions. So I think the biggest notable omission is memory. We have no RAM, we have no cache, we have no storage, at least in a quantum sense. In fact, the first one, RAM, this is going to be a huge thing in quantum computing. At the minute, this is effectively a stack machine, whatever you want to call it. You load up a buffer of instructions and you hit play, and they run and you get an output. If we get quantum RAM, our ability to speed up algorithms and run algorithms better just explodes. It's a real, and there's a huge number of efforts in quantum RAM, and if we unlock that, it'll be incredible. Currently, there is no quantum hardware provider that also has quantum RAM. So we also have cache or storage. Storage is another one because a fun fact about working with quantum information, you cannot copy it. You cannot do copy-paste on a quantum piece of information. If you have many copies of it, there are many scenarios where you can, some like subcases, but in general, there is no sense in copying. So you cannot just copy it to disk and then reload it later. You could have to, you can store some classical representation. As you see, there's no GPU. This is, bit string output and I/O. We don't have an operating system where you play around and it's being run on a quantum computer. You send us the instruction sets and you give it back. Oh, cool. So that's where we are today. That's where hardware is at today. So there's a lot of proof of concept work going on in quantum computing and the hardware. And moving beyond that, this is just we're in the NISQ era, noisy intermediate scale quantum computing. So coherent times aren't as long as there was a question earlier. Coherence times aren't as long as we'd like. Error correction will come up next. We need more qubits for error correction. On the hardware level, it's basically the two problems we have are scaling and noise. Noise is something we cannot escape, so we'll look at how we can mitigate it. And scaling is a challenge that every quantum company is looking at. At Oxford Quantum Circuits, I showed you our core IP is around the horizontal scaling of our qubits, so we think we've got that covered. Future plans. So if I put this first, because it's what I'm working on and excited about, the next generation of compiler infrastructure. Better optimizations, more interoperability, and data structures. There is no quantum list, there is no quantum hash map. There's some work on this, but this is bit level. We need to think about abstractions that let people just start writing code and picking up quantum algorithms. There's, roughly speaking, two approaches on this. There are some projects that look at, if anyone's familiar with CUDA, writing CUDA code, you have separate CUDA functions that say this is for GPU, do your GPU bit here, which you can do on quantum computing. Say, this is all classical compute, this bit, do it quantumly. Or the dream world is that you just write Python, and it will split out any good quantum bits and any good classical bits. There's a company called Horizon Quantum that are developing compiler architectures looking at doing exactly this. They're taking Octave and splitting it quantum and classically. Scale the number of qubits. Next one. We need more bits. We're at 8 bits. We'd like a lot more than that. Quantum error mitigation. So this is preventing errors as they occur. So one thing you can do is, let's say you have high readout error, where your zero state is highly biased in your readout error. You can randomize your compilation. So you add these random angles in that randomizes your outputs, and that's a way you can mitigate this 0-1 bias, for example. Quantum error correction, I've left till last, because I think this is going to be, this is the biggest challenge for all quantum hardware providers. It's an incredible topic, an incredible idea that by entangling qubits, you take one bit of information and spread that in a highly entangled state, you can hide your information from nature. So that if the environment comes in and starts impacting your information, you haven't lost all your information in one go. We are distributing our information across many, many bits. Simplest, repetition code. 0 goes to 000, 1 goes to 111. This, is still used in a lot of classical compute, where there are quantum error correction codes that can correct for all the different quantum errors that can occur. And this is going to be a huge challenge to scale. When we hit, there's a figure going around a lot lately, that when we hit 1 million qubits, we're going to be generating around 1 terabyte of data a second in terms of output, testing it, correcting it. That's a lot of information for a single computer to fit in one room. So that's where a lot of the challenge for classical control stack is going to be, just throughput. Hitting 1 terabyte per second through a bunch of FPGAs is quite a challenge. Yeah. And we're in a bit of a Cambrian explosion of quantum error correction at the minute. Every day there's new results coming out, and people are reaching the point where we're actually extending the lifetime of a quantum computer with error correction. And then more direct connect to cloud providers, bringing quantum computers to as many people as we can, bringing it to more people is something very keen on. And Oxford Quantum, we're expanding into the Asia Pacific region as well. So we're trying to bring it everywhere. Yeah. And Mark said no sales pitches. I'm sorry. My company sent me here and they paid for my trip to DEF CON. A sales pitch. We are hiring. Come and join us. I love it. Come and speak to me. I'll speak to you candidly because I love my job. It's incredible. I get to build quantum computers for a living. It's kind of wild. And thank you, yeah. We see a brighter future for all enabled by quantum. End of my talk, and any more questions? Are my slides available? I think this talk is recorded. Yes, it's recorded, yeah. We're all good, recorded. So yeah, the recording will be available. Cool. Yeah. Yeah, so the question was about an issue with old RAM where operations on one bit were being affected other bits next to it. And this is exactly the sort of errors that people see in quantum computing, and exactly the kind of errors that quantum error correction will correct for. There is a big challenge with highly correlated errors like that. So if multiple qubits get an error in a highly correlated way, that's a real challenge. That's big. Uncorrelated errors, we sort of know how to deal with. Challenges like that will be very, very difficult. Yeah. Yeah, so the question was around we're at millikelvin. Can we push it further to improve our coherence times? Yes, but diminishing returns, exactly as you say. I think it's what we're better spent right now on improving our calibrations and our operational stability and that sort of thing. But yes, that is, we'd be at 0 if if we could. So, cool. Well, I'll be around the Quantum Village, so ask me questions anytime if you have any. Thank you all for listening and your questions. Cheers.